Continuation of chapter 4, that is inverter. In the last session, I discussed about what exactly single pulse width modulation technique. But the problem with single pulse width modulation is what is the drawback? At a time only one harmonic is eliminated. That's the reason why we are implementing multiple pulse width modulation technique. Okay. Next concept is very important. Multiple pulse width modulation technique. Adam, all of you. Multiple pulse width modulation. Yes. What do you mean by multiple pulse width modulation means? The number of pulses per half cycle is greater than or equal to 2. Then we can say that is called multiple pulse width modulation. That is number of pulses per half cycle. If you generate the number of pulses per half cycle is greater than or equal to 2, then we can say that is multiple pulse width modulation technique. Then what is the need of generating the more number of pulses per half cycle? Yes. The point to remember, in a single pulse width modulation, at a time only one harmonic is eliminated. That is low order harmonic. But at a time you want to eliminate the more number of harmonics, then it is required to generate more number of pulses per half cycle. Yes. That is, if the number of pulses per half cycle is increases, the order of harmonics associated with output is increases. I am not talking about number of harmonics at output. I am talking about order of harmonics. That means output consists of only higher order harmonics. Then all the low order harmonics are eliminated if we generate the more number of pulses per half cycle. That is output associated with higher order harmonics. Then there is no problem with the higher order harmonics. Why? The more dominant harmonics are low order harmonics only. If all the low order harmonics are increases, if the output consists of only higher order harmonics, those harmonics can easily filtered by using small size filter. Understood? That is the reason why we want to generate more number of pulses per half cycle. That is, if number of pulses per half cycle, if number of pulses per half cycle increases, if number of pulses per half cycle increases, output order of harmonics associated with output is increased. That is, output consists of higher order harmonics, and all the low order harmonics are eliminated. Okay, this point to remember. All the low order harmonics are eliminated. That is, for example, if there is 5 number of pulses per half cycle, let us assume that output consists of order of harmonics is 23, 25 and so on. Now what I am doing, when I generate the, just example I am telling, just understanding, this is not exact harmonics. When I generate the 8 number of pulses per half cycle, then output may consist of 31st, 33rd like this. That means if the number of pulses per half cycle is increases, then order of harmonics at output is increases. Once the order of harmonics at output is increases, those higher order harmonics can easily filtered by using small size filter. That is, all the low order harmonics are eliminated. Then if any higher order harmonics are present, eliminated, then higher order harmonics are easily filtered by using small size filters. That is the purpose of implementing multiple pulse width modulation technique. Now the question is, you want to generate more number of pulses per half cycle. Then how to generate the more number of pulses per half cycle? To generate more number of pulses per half cycle, we can use one control circuit. That point also remember. To generate more number of pulses per half cycle, to generate more number of pulses per half cycle, a control circuit is used. Okay. A control circuit is used. Then what the control circuit consists means? A control circuit consists of comparator. This is a control circuit we are using. Comparator. The input to the comparator is two types of inputs we are giving. One is reference signal input, and another one is carrier signal. Comparator is having two input, one is reference signal and carrier signal. The output of the comparator is given to trigger circuit. Yes. The trigger circuit will generate the pulses to switches. It generates the pulses to switches. We can use some logic in comparator. According to that logic, it compare reference signal and carrier signal, then which activate the trigger circuit. Then the trigger circuit will generate the pulses to switches. Okay, this control circuit we can use to generate the more number of pulses per half cycle. But point to remember, to get more number of pulses per half cycle, always you maintain carrier signal frequency must be greater than reference signal frequency. That means to get more number of pulses per half cycle, always carrier signal frequency, that is FC, is greater than reference signal frequency FR. You must maintain carrier signal frequency greater than the reference signal frequency. Then to maintain carrier signal frequency greater than reference signal frequency, in general, triangular wave is taken as a carrier signal. But reference signal depends on type of PWM technique. Type of PWM. That means, in general, to maintain carrier signal greater than the reference signal, in general, triangular wave is consider as which signal? Carrier signal, and reference signal depends on, and reference signal is taken based on type of PWM. But this is the selection of reference signal and carrier signal. For example, if you take a type of PWM and reference signal, carrier signal. If it is multiple pulse width modulation, then which is the reference? The reference signal is rectangular wave. Or you take square wave also. Then which is the carrier? Triangular wave is the carrier. If it is sinusoidal pulse width modulation, which is the reference? Sine wave is the reference. Then which is the carrier? Triangular is the carrier. If it is a trapezoidal pulse width modulation, which is the reference? Yes, trapezoidal is reference. Which is the carrier? Triangular is carrier. Like this we can. That means, based on the type of pulse width modulation, the reference signal is changed. But always which signal is carrier signal? Triangular wave is carrier signal. Why we are maintaining the carrier is triangular? Always to maintain carrier frequency greater than reference frequency. What is the need of maintaining carrier frequency greater than reference frequency? Yes, to generate the more number of pulses per half cycle. What is the need of maintaining the more number of pulses per half cycle? Then if you generate the more number of pulses per half cycle, then all the low order harmonics are eliminated. Then output consists of which harmonics? Only higher order harmonics. That is, order of harmonics at output is increased. Okay. Now let's see, per half cycle, how many pulses are generated in the case of multiple pulse width modulation? How we can calculate? Okay, that I want to explain by taking one example. Okay, let us consider how many number of pulses per half cycle is generated in multiple pulse width modulation. Is it over? Quick. This 3 points. Now see, how many number of pulses per half cycle is generated by using multiple pulse width modulation. Okay, let us consider this multiple pulse width modulation. I am taking the carrier is triangular wave. This is carrier signal. For half cycle I taken 3 cycles of carrier. For negative half cycle also I am taking 3 cycles of carrier. Okay. Let this is reference wave. This is carrier wave. Okay. Now take the rectangular is reference wave. One cycle of reference wave I am taking here. These two are applied to which one? Comparator. Yes. The amplitude of carrier signal is Vc and the amplitude of reference signal is Vr. That this is Vc and this is Vr. Yes. This minus Vc and this is this minus Vr. This is minus V. Okay. Then what logic we are using here? If Vc greater than Vr, pulse is generated, then output is positive. Positive pulse you can get. If minus Vc greater than minus Vr, pulse is generated, then output is negative. This is the logic we can apply. Okay. Then these two signals are given to comparator, then you can generate the pulses. Yes. Here one pulse is generated. Vc greater than Vr. Here also one pulse is generated. Vc greater than Vr. Here also one pulse is generated. Vc greater than Vr. Okay. Here also pulse is generated. Here also pulse is generated. Minus Vc greater than minus Vr. We are getting negative. Okay. If you take on omega t axis, you take on omega t axis. Okay. Then here the pulse is generated. Here also pulse is generated. This is positive pulse. Here also pulse is generated. Sorry. Here also pulse is generated. Okay. And here the negative pulse is generated. And here the negative pulse is generated. Here the negative pulse is generated. Okay. Then this amplitude is Vs and this amplitude is also minus. Then how many number of pulses per half cycle? 3 pulses per half cycle. Then what the each pulse width you tell me? Yes. This is 2d by 3. Yes. This also 2d by 3. This also 2d by 3. This also 2d by 3. Each pulse width is 2d by 3 because the number of pulses per half cycle is 3. For n pulses, each pulse width I given a 2d by n. Like that, it is 2d by 3. Okay. Now, but I want one generalized formula. Here, based on carrier signal and reference signal, here how many pulses are generated? 3 pulses. If you change this carrier signal, automatically the number of pulses per half cycle is generated is also changed. Okay. But we want generalized formula means, listen please. How many carrier signals are considered in 1/2 cycle? 1, 2, 3. 3 carrier signals. Then what is the total time period here? Each carrier signal time period is Tc. Okay, this is also each carrier signal time period is Tc. Each carrier signal time period is Tc. But how many reference signal we are taken? One reference signal, one cycle of reference signal. But this is half cycle of reference signal now. With respect to reference signal, what is the time period? Tr by 2. Okay, can equate like this? 3Tc equal to 3Tc equal to Tr by 2. Yes. Then what is the 3 by Fc equal to 1 by 2Fr. Then what is Fc by 2Fr? Fc by 2Fr equal to 3. This is number of pulses per half cycle. Per half cycle. This is according to formula I am getting 3. Here also what is this 3? Number of pulses per half cycle. Therefore, number of pulses per half cycle in multiple pulse width modulation. How many number of pulses per half cycle? The number of pulses per half cycle n equal to Fc by 2Fr. This is a generalized formula. Very important formula. What is FCR? Carrier signal frequency. Yes. Carrier signal frequency. What is FR here? Reference signal frequency. Reference signal frequency. Like this, how many number of pulses per half cycle it is? Okay, like this we calculate. So this is about what exactly multiple pulse width modulation technique. But I want to apply whatever the multiple pulse width modulated output we are getting. This multiple pulse width modulated output is not a sinusoidal. Okay, that is not a sinusoidal. The fundamental component is sinusoidal. This is non-sinusoidal. Any non-sinusoidal waveforms are analyzed by using Fourier. Yes, sir. Now we'll see what the Fourier analysis of multiple pulse width modulated output. Yes. Put siding. Fourier analysis of Fourier analysis of multiple pulse width modulated output. Yes. Or the Fourier analysis of multiple pulse width modulated output. Let us consider this is a multiple pulse width modulated output. To take any number of pulses. This one of the multiple pulse width modulated output. Yes, take this. How many pulses per half cycle? 3 pulses per half cycle. Three pulses per half cycle. Let this is pi. The another half cycle is 3 pulses. In the negative half cycle also 3 pulses are there. Like this we are. So this is multiple pulse width modulated output. Okay. This is 2 pi omega. Okay. Now let each pulse width is 2d by n. If you assume that I want one generalized formula, that's why I taken each pulse width is how much? Each pulse width is this one. 2D by n. Okay. Then let this I taken as a some constant gamma. Taken this some constant gamma. Okay. This is some constant gamma. Gamma is some constant here. Okay. Where gamma is the constant. One observation here. This 1/2 cycle. How many pulses are generated? 3 pulses. This pulse width, this is each pulse width, each pulse width, each pulse width. But this is space width. This is space width. This is space width. This is space width. 1/2 cycle. If there is a 3 pulses, how many space widths are generated? 4 space widths are generated. 1, 2, 3, 4. That means for n number of pulses per half cycle, for n number of pulses per half cycle, number of space widths equal to number of space widths. How many number of space widths? N plus 1. Number of space widths equal to n plus 1. Now listen please. Then what is the space width I want? Each space width equal. Each space width equal. Tell me. What is the each space width? This is total is gamma. This is 2D by n means what this one? This is d by n. Okay. This is symmetrical about this. Then this is total 2D by n means d by n, d by n. D by n plus d by n, 2D by n. Then this total is gamma, this is d by n. Then what is each space width? Gamma minus d by n. Gamma minus d by n. Each space width. Then what is the total space width? Total space width equal to how much? Yes. Total space width equal to gamma minus d by n into n plus 1. Because n plus 1 space widths are there. Okay. Then this is the total space width. Now tell me. This total is pi now. This total is pi means now from this tell. If total is pi means this total is pi, shall we equate like this? Pi equal to space width plus space width, total space width plus total pulse width. Total pulse width. All this gives the pi. What is the total space width? N plus 1 into gamma minus d by n. Yes, gamma is constant. Gamma minus d by n. Plus, what the total pulse width? If it is a 3 pulses means 2d by 3 plus 2d by 3 plus 2d by 3. Total how much it gives? 2d plus 2d. Then from this, gamma minus d by n equal to, shall you write like pi minus 2d by n plus 1. Then from this, gamma equal to pi minus 2d by n plus 1 plus n plus 1 by plus d by n. This is how to calculate constant gamma. This gamma is measured from 0 to half of the pulse width. From this reference to from this angle. This is measured as a gamma. This is one constant. Pi minus 2d by n plus 1 into d by n. Okay, this one point you remember based on multiple pulse width modulation. That depends on gamma value depends on number of pulses per half cycle. Where n equal to what is capital N here? Number of pulses per half cycle. Number of pulses per half cycle. Yes. Now see, one more point, one more observation. Listen please. In a multiple pulse width modulation, whatever we are getting multiple pulse width modulation, take one pulse. This is one pulse. Na? I want each pulse width. I want to calculate each pulse width. Then this is which signal? Reference signal. This is which signal? Carrier signal. The carrier signal reference is that. Okay, this carrier signal. Let's take this is the reference. This is the total pulse width. This total is pi. If there is a n carrier signals like that, then each width of this one is pi by n. If n carrier signals are there, then you take pi by n. This total width is pi by n. Okay, shall we write like this? Let this point is, this is A, this is B, this is C, this is D, this is A, this is O, and you draw one perpendicular line here. Let this at midpoint. From this midpoint, we can draw one perpendicular line. This O, A, let this is M. This point is M. There is a two triangles. Triangle ADE is one triangle. Triangle ABC is another triangle. These two triangles are similar triangles. Then according to similar triangle principle concept, if any one vertical line is drawn from the midpoint, then how to write? OA by AM equal to, and these two are similar triangles means, then how to write? DE by BC. OA by AM equal DE by BC. According to similar triangles. ADE is one triangle, ABC is one triangle. What is OA, you tell me? This total is VC. And this is VR. Then what this one? VC minus VR. That is VC minus VR by, what is AM? AM is nothing but total. That is VC is equal to, what is DE? This one. DE is nothing but a pulse width. Na? This indicates the pulse width. That is pulse width by each pulse width. This is each pulse width. Each pulse width by, what is BC? Pi by n. Pi by n. Okay. Now from this, you tell me what is each pulse width. From this, what is the each pulse width equal to? Now, I am calculating like this. This over na? Yes, complete this. Then what is each pulse width, you tell me. Then each pulse width equal to, from this, each pulse width equal to pi by n into, this is 1 minus VR by VC. This is a formula. In a multiple pulse width modulation, how to calculate each pulse width? Pi by n into 1 minus VR by VC. Okay. Where VR by VC is called amplitude of reference by amplitude of carrier. Amplitude of carrier. This ratio is called modulation index. It is called modulation index. In general, modulation index means you take amplitude modulation. If it is not mentioned that if it is a frequency modulation or amplitude modulation, generally you take a modulation index means you take the amplitude modulation. This is called modulation index M. Where M equal to VR by VC, that is called amplitude. Therefore, each pulse width is also written like this. Each pulse width equal to pi by n into, one more formula for each pulse width is 1 minus m. If modulation index is given, how to calculate each pulse? Like this we can. This how to calculate gamma, then how to calculate each pulse. These two formulas. Okay. Now, for this waveform, you want to apply Fourier analysis. Now, with this knowledge, I don't want to derive the Fourier analysis directly. I'm writing the formula for multiple pulse width modulation. You tell me. Okay, this over now. You tell me. If Fourier analysis is applied for the above waveform, this one multiple pulse width modulation. For this waveform, if Fourier analysis is applied, because it's a non-sinusoidal, analyzed by using Fourier. If Fourier analysis is applied, then what you can get applied? So then according to Fourier analysis, the instantaneous output voltage V0 equal to, this is V0. The instantaneous output voltage V0 equal to, how to write A0 plus summation n equal to 1 to infinity an cos n omega t summation n equal to 1 to infinity bn sin n omega. This is according to Fourier analysis. Then for this waveform, if you calculate A0 and An and Bn values, A0 is 0. Then An is also 0 because of half wave symmetry that you know in mathematics. An is also 0. Then we can define only Bn. The value of Bn equal to, here I am giving for n pulses. Generalized formula I am giving n into 4 Vs by n pi sin n gamma sin nd by 2. Yes, sorry, sin nd by n. 4 Vs by n pi sin n gamma sin nd by n. This is the value of Bn for n pulses. For n pulses, this is a formula for half cycle. Only Bn is defined. Now this is defined only for n equal to 1, 3, sorry. For n equal to, this is defined for n equal to 1, 3, 5 and so on. For all this Bn equal to 0, for n equal to 2, 4, 6 and so on because of half wave symmetry. Now you substitute An, Bn values in this equation, then what we can get? This over now. What is the gamma that you know? That is, by substituting this, the instantaneous output voltage in multiple pulse width modulation V0 equal to yes, n into summation n equal to 135 up to infinity 4 Vs by n pi sin n gamma yes, sin nd by n sin n omega. Okay, this is the formula for instantaneous output voltage for multiple pulse width modulation technique, where gamma equal to pi minus nd by, that is pi minus 2d by. But I given this, okay, that we calculated now. What is the value of gamma? Gamma equal to, what you are getting? Pi minus 2d by n plus 1 plus d by n. For example, if you want to write this formula for, this is applicable for any number of pulses. This formula is applicable for any number of pulses. If you want to write this formula for single pulse width modulation, for single pulse width modulation, what is n equal to 1? Then what is gamma? Gamma equal to single pulse width modulation, n equal to 1 now, pi minus 2d by n equal 2 plus d by 1. Then what is you get? Pi by 2 minus d plus d. How much you get? Pi by 2. Then what is instantaneous output voltage? V naught equal to n equal to 1 you substitute. Summation n equal to 135 up to infinity 4 Vs by n pi sin n pi by 2 sin nd sin. This formula I given in single pulse width modulation, we are getting same formula as per. That's why no need to remember for different pulse width. Just no need to remember for different pulses for half cycle. Then you remember this, in that you can substitute, then you can get single pulse width modulation formula. Then for example, you want to write the formula for 2 pulses, for 2 pulse width modulation technique. If n equal to 2, what is the formula you can get? If n equal to 2, you can substitute. If n equal to 2 means, then what is the gamma you can get, you tell me? Gamma equal to pi minus 2d by 2 plus 1 plus d by 2. And what is gamma equal to? Pi by 3 minus 2d by 3 plus d by 2. Then what is the gamma equal to? Pi by 3. Yes, this how much we can get? Minus 2d by 3 plus d by 2. Then how much you get? This minus, this is by simplifying this one, minus this minus 4d plus 3 minus d by 6 we can get. Okay, this 6 times, that is 3 times, that minus d by 6. Then gamma equal to, then what is instantaneous output voltage? Summation n equal to 135 up to infinity. Then n equal to 8 Vs by n pi. 8 Vs by n pi sin n into pi by 3 minus d by 6 sin nd by 2 sin nd by 2 sin n omega. This is a formula for which one? 2 pulse width modulation. Like this, if you want to write any number of pulses for half cycle, then we can remember this part. Then from this we can write any formula also. Then what is the instantaneous value of output voltage? If you want to write instantaneous value of output voltage, maximum value of nth harmonic output voltage means 4 Vs by n pi into sin n gamma into sin n nd by 2 into nd by n into n. Okay, the maximum value of n without function, this gives the maximum value. If you want RMS value means by root 2. If you want to fundamental means you substitute n equal to 1. You know how to write the formula. Okay, for example, in a multiple pulse width modulation, maximum value of nth harmonic output voltage, if it is asked. Okay, mainly this formula you remember, this gamma you remember, these 2 formulas. Here I given for n equal to 1 this formula. This is for single pulse width, for 2 pulse width. Then in general, if you want to write means, what is the maximum value of nth harmonic output for n pulses? Okay, maximum value of nth harmonic output. Maximum value of nth harmonic output. How to write? Maximum value of nth harmonic output. Nth harmonic output. What is the formula, you tell me? Then V naught Nm equal to n into 4 Vs by n pi sin n gamma sin nd by n. If you want RMS value of nth harmonic output, V naught Nm by root 2. Then you want RMS value of fundamental, V naught RMS value of fundamental means this is how much? N into 2 root 2 Vs by n pi sin n gamma sin nd by n. If you want to write what is the RMS value of fundamental, substitute n equal to 1. n into 2 root 2 Vs by pi. N is nothing but a harmonicum, not capital N. Capital N is number of pulses per half cycle. Sin gamma sin d by n. Like this we can. This is RMS value of fundamental. Like this we can write any formula. Okay. Okay, this about what exactly? Multiple pulse width modulation technique. Clear? Concentrate. In the next session, we will continue with what is the sinusoidal pulse width modulation technique. After that, and in a sinusoidal pulse width modulation, what is unipolar switching? What is the bipolar switching concept? Also, I want to be okay. Clear? Concentrate. This about in detail about multiple pulse width modulation. How? What are the number of pulses per half cycle in multiple n equal to fc by cfr? How to define modulation index? Modulation index is defined as VR by Vc. VR by Vc is nothing but a modulation index. Generally, modulation index means you take amplitude modulation. If it is mentioned that frequency modulation, then only take. What is the frequency modulation? I will define later after discussing sinusoidal pulse width modulation. All those items. Clear? Concept.